Hello and welcome to another video. In this video we're going to be working on valid parentheses string. And in this problem you're given a string consisting of three types of characters, open and close and a wildcard, and return true if s is valid. So they just tell you like what needs to be the case for parentheses, and and the wildcard can be a left or right parenthesis or nothing. So these are the things that we talked about yesterday to make the rules for a parenthesis, right? So there's two rules for valid parentheses. Every right parenthesis must have a corresponding left parenthesis come before it. And every left parenthesis has to have a matching right parenthesis. So essentially what this means is the count of left and right parentheses have to be the same. And you at any point in the actual string, there can't be more right parentheses than left. So for example, if we have two left, now we're only allowed two rights. And then the next one has to be a left, and so on. So we can't have something like this. So I'll talk about two solutions. One's pretty straightforward, and then one I didn't come up with. I just looked at some other solutions because it's pretty hard to come up with, to be honest, in my opinion. So the easy solution is actually just memoization. So let's first look at these examples. So this is true. This is true because this wildcard can just be an empty string. And then here, this is also true because this wildcard can be a left parenthesis. But we can't do some things like just count up the number of left and right and then just like see if the wildcard can make up the difference. Because like, what if we have this? And then we have like the wildcard. So I'll just draw a star instead. So let's say we have like star, star, star. Something like this, right? So the wildcard can make up the difference here, right? Like there's three right, two lefts, and we can maybe say like, well, we can just, the wildcard can be a left. But that doesn't work because we still have like unmatched right parentheses. So the left parenthesis has to come before the right. So the order of these wildcards matters because like this is invalid. But if we just take these wildcards and put them over here, now all of a sudden this is fine, right? So, and so on. So like the order of the wildcards actually matters. You can't just like count these things up. And so because the order of the wildcard matters, let's talk about two solutions that one should be like pretty straightforward, just a pretty straightforward dynamic programming one, especially because the constraints are pretty small. So it's pretty straightforward dynamic programming. We need three things. So we need a state, base case, and recursive. So for state, pretty straightforward what you need, right? You just need to maintain like the difference of left and right parentheses. So you can either have like a number of open parentheses and number of closed parentheses that you've used so far, or you can just have one variable, kind of like we did in the problem yesterday, called like total, where an open parenthesis is worth 1 and a closed parenthesis is worth -1. And then we just keep track of the state and we just check what character we're on. So if we're on a left parenthesis, we can just always try it, right? We pretty much have to try it, in which case our recursive case here would be pretty easy. It would just be, so if we have an index and a total, for the left, the dynamic programming solution would just be go to the next index and do total plus 1, right? As in like one more left. Then for the right, whenever you encounter a right, you have to make sure that your total is greater than 0 to begin with, right? Because you can't have a 0 total, because 0 total means you have the same number of left and right before this right, in which case it's just being valid. So for example, we have something like this, which is a total of 0, and then we run into a right. This would not work. So, and then if our total is greater than 0, then just recurse and make total -1. So pretty easy. And then for the wildcard, you just try all three. But before trying the right, you also make sure this case here. So you can only make it a right parenthesis if the total is greater than 0. So you just recurse to all three, empty string or left or right, and then see if any one of those gives you a valid result. And if any one of those gives you a valid result, then you should return true. And so I'll briefly talk about the time and space, and we can just move on to the next one. I'm not going to code it. It's pretty simple. So our state here would be like I total, which index, so the total can be like 100, and then the I can be 100, so this is n squared. Yeah. And then the space will also be n squared. You can cut down the space to O of n just by doing bottom up and getting rid of this dimension, because every recursive case will be like I plus 1. So you can get rid of this dimension, in which case you'll have n squared time and n space if you want to. But let's talk about another one that is a lot harder to come up with, in my opinion, and it involves stacks. So let's just think about like what we have to do. So let's say we have some random parentheses, like we just have some random parentheses like this, and then we run into a right parenthesis. Well, if we run into a right parenthesis, where is its matching left parenthesis going to be? So its matching left parenthesis is just going to be like the rightmost left parenthesis, right? It's going to be over here. Yeah. And so what we can do is we can just have a stack of indices of left parentheses. And also, so let's say we have left parentheses, but we also have wildcards. So we can use a wildcard for a left parenthesis as well, right? Or we could use it for a right parenthesis. So what we're going to do is we're going to have two different stacks. And we'll have one stack of left parentheses, and then whenever we reach a matching right parenthesis, like let's say we had no wildcard at all, right? So let's say we just had something like this. This would be pretty easy. So we can just have a stack of left parentheses. So let's we'd have like left, left, left. So we'd have, a stack of 3 of them. And then whenever we reach a right one, we're just going to pop off like the closest one, because that's going to be the matching parenthesis, right? Because these two match, these two match, these two match. So whenever we reach a right, we can just pop this off. Then we reach a right, we pop this off. Then we reach a right, pop this off. But we can also use wildcards. So what we're going to do is, instead of just like keeping track of how many we have, we're going to store an index of where every single one of these occurs, and then where every single wildcard occurs on a stack. So let's make an example of this. So let's just have our actual input, and then we can have some stacks. So let's say we have like open, and then we'll have a wildcard, and then an open, and then closed, open, closed, wildcard, open, closed, wildcard, or something. I don't know if this will work, but let's just try this one. Well, it'll obviously work, but I don't know if it'll be like valid or not. So let's have our two stacks. So we'll have a stack over here, and we'll have another stack over here. And so the two stacks we're going to keep track of is, like I said, we're going to keep track of open parentheses and wildcards. Because whenever we reach a closed parenthesis, we never need to like put that on a stack, right? We just check like, is there an open one to match? But whenever we have an open or a wildcard, we need to keep track of that. And also, we might need to use wildcards for closed parentheses. So we're going to try to use them for opens to start off, and then we're going to try to use them for closed. So let's walk through what this will look like, essentially, with these two stacks. So we'll call this stack open parentheses, and we'll call this wildcards. Okay. So we're going to go to this first thing, and we're going to check, okay, well, this is an open parenthesis. So where does it occur? It occurs at index 0. So we're going to store it. That's the thing. We need to store the index of where it occurs, because in order for these wildcards to work, like for a wildcard to match a closed parenthesis, like let's say we're trying to match this. We can't match this with this one over here or this one over here, right? It has to be the one before it. That's why we need to actually store the index. And the same thing, if we're trying to match this one, this wildcard, we can do that, but we can't match like this and this, for example. So that's why the indices matter. Okay. So let's and the stack will work, because for any closed, you just need to know how many parentheses are after it. So ideally for this one, for example, you want to use this wildcard, right? You want to use the one furthest down first, and that's why the stack will work. Okay. So yeah, so let's walk through this. So here we have an open, so we're going to store index 0. Then we have a wildcard, so we're just going to store the wildcard, and let's put this in wild. And then if this example isn't great, we'll come up with another one, but hopefully this one's fine. So this will be at index 1. And then we have an open, so this is at index 2. Okay, so now we have a closed. So, and we can have this just to show where we're at. So we have a closed. So first we try to match it with an open, because we want to try to use up as many open parentheses as we can, because that way we don't have to match them later, right? We ideally want to match opens, and so we don't have to match, so we don't have to like close them later. So like I said, in a normal parenthesis, which one would it match with? It would match with this one. That's the one at the end of the stack. So what's going to happen here is we're going to look over here. We have a closed, and then we're going to check, is our open and our wildcard parentheses non-empty? If both of these are empty, then this is like invalid, right? Because there's nothing to match it with. So we're going to match it with our open parenthesis. Then we have an open, so we're going to put this on. Then we have a closed, so we're going to pop this off. Then we have a wildcard, so we are going to put this on here. So this is index 6. Then we have an open and close, so it will just push it and pop it off. Then we have wildcard again. This will be at index 9. And now, so we've matched every single closed parenthesis, right? But we still have this one that we didn't match. So now, all we have to do to match it is just say, is there a wildcard that's after this one? So if we have a bunch of unmatched parentheses, for each one of them, we want to use the wildcards after them, right? So for this one, we're just going to check, is there a wildcard after it? And ideally, because we're going to be looking through our parentheses backwards, right? Like let's say we're trying to match like this one and this one and this one. Ideally, we want to match like as far down as possible to start off. And that's why the stack works really well, because you're going to match your open parenthesis with the farthest one down. So that way it's possible. Because let's say, so this one's pretty easy, right? Like we'll say like, okay, we can match this with this wildcard here, which we can. And so that would mean that if we turn this into, if we turn this into a closed parenthesis, this would be a valid solution. And that would indeed be a valid solution, right? These two match, these two match, these two match, and these two match. But let's say, like just to show you an example, let's get rid of all these. And let's say we're trying to match a bunch of like open parentheses. So we're trying to match like this one and this one. Obviously, this isn't going to be in like our actual thing. So let's say these are our open parenthesis locations that we have still yet to match. And let's say our wildcards are here, 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 and here. This is what I was talking about. You want to match this with this one because this is the only one it can match with. So even though this one can match with a bunch of different ones, you want to match the ones that are further down first, because that way, like let's say I match this one over here in my code. Well, then this wouldn't exist, and now I can't match this with anything. So that's why you want to match the parentheses that are further down first with the wildcards that are further down. That's why the stack works really well. So let's maybe do like one more example that's like a little bit, has a bit more wildcards, and then we can be done. So let's just say this is open again. And let's say this is open again. And then let's have like wildcard, 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 closed. Let's have more open. So maybe something like this, and then like wildcard, wildcard, something like this. Okay, so let's walk through this one, and then we'll pretty much be done. But yeah, this is kind of hard to come up with, to be honest. And I think when you see the example, it makes it a lot like clearer why use a stack. But coming up with it from scratch is pretty hard. And I do think that the memorization is pretty easy. Okay, so let's walk through this one. So here we have an open, so we're going to mark index 0. Then we have an open again, so we're going to mark index 1. So we have 3 wildcards, so we're going to put those in, so 2, 3, 4. Okay, then we reach a closed. So for this closed, we're going to see, okay, do we have one that's open? And like I said, the ideal one you want to match it with is the one right next to it. So the one farthest to the right, because those are going to be the hardest to close. Because in order to close a parenthesis, you need a wildcard. Like if we do close parentheses with wildcards, you need wildcards after it. So that's why it's in your best interest to match the farthest one down, because the ones that are closer to the start will be easier to close. Okay, so we're going to close this one. Yeah. Okay, hopefully I can delete it. All right. So then we have 2 more opens. So we have 6 and 7. And then we have 2 more wildcards, so 8 and 9. So then same thing. These are the open parentheses that we have not closed, so 0, 6, and 7. So we're going to close this one with this. And like I said, you just check, like whenever you have a parenthesis here, you need to make sure you have something in the wildcard, and that index needs to be greater, right? So because this is increasing, like let's say this was not 8, 9, let's say this was like 5, 6, then you'd have a false because none of these wildcards are past this parenthesis. So you wouldn't be able to ever close this one. So yeah, so this one we can close. So we can close it here with this. And then the 6 we can also close. And then the 0 we can also close. So we basically take our last 3 wildcards, turn them into closed parentheses. And that should give us a valid parentheses. So we have like open, open, close, close, open, open, close, close, which is valid. So that's kind of the idea behind it. like I said, I think it's pretty hard to come up with. I think if this was like an interview question, I would just do memoization, and it is important to realize that like you can't just count these up. The location matters. That's why you need to use a stack. There's also like an in-place one that's even more confusing in my opinion, so I think this one's like a little easier to follow. So yeah, let's code this one. So essentially we're going to have a stack for our open parenthesis locations and a stack for our wildcard locations. And we can just use in Java, we can just use like a integer or a list. So we can say this integer, because arrays in Java are static, so we can't do that. So we can just use, so this is going to be like opens, and then array list. Oh yeah, I turned this on. It's kind of helpful for Java, where it'll give you like autocomplete, so you could look at actual like the best methods to use, because there's so many. Yeah, so then we also have list integer wildcards. We call this like wild. Okay, and then what we need to do is we need to go through our string and check if it's open, closed, or a wildcard. So we can just say this. Oops. Okay. So essentially we're going to check for these three things. So we can say like if, we'll start with the open equals open. So if it's open, we're just going to add it to our stack of opens, and then we're going to clear at the end. So we can say opens, and we can look at, so we're going to be using add here, and then this is going to be, we just need the index, so just I. So next case, we'll do closed, or we'll do wildcard, I guess, actually. It doesn't really matter. Like, let's do wildcard. So, because open and wildcards are like the similar logic. So if it's a wildcard, same thing, just add it to the wildcard. Okay, and then finally, elseif. Okay, so finally, it has to be a closed now. So if it's a closed, first we check, is there something on the opens? So we can say if opens, so you can use is empty here. So if it's not empty, let's just pop that, and then that's the one we're going to close it with. And because we're going in order, the last item on opens is guaranteed coming before this one here. So if this is the case, we can just pop, so opens. I think it's like you can use remove last, I believe is one of these. Yeah, remove last. So we just get rid of the last item, and there we go. So if the parentheses doesn't have anything, then we need to do the same thing for the wildcards. So this is all the same, just for the wildcards this time. So this is going to be wild, it's empty, and we pop from there. Otherwise, if we have no opens and wildcards to pop from when it's a closed, then we just can't match it, so we just return false. Okay, so now that we went through this, yeah, now that we went through this, I guess the spacing is kind of weird here. We might still have like open parentheses that are unmatched. So we have to match every single open parenthesis that we have left. So let's do that next. Yeah, spacing's like this. Screwed up. Okay. So essentially we can just say like while we have open parentheses, so while opens, you can use the is empty again. So while it's not empty, we are gonna check is the wildcard thing not empty as well? So we have to match it with a wildcard, and the wildcard location has to be past the open parenthesis, right? In order to match an open parenthesis with a closed parenthesis, the closed parenthesis has to come after it. So we can say if, so we can just have the case here for returning false. So we can say like if wildcard is empty, or the last element of wildcard is smaller than the last element of opens. So we can say wild, I think there's a get last or something. Yeah, so wild get last is less than opens get last. So if that's the case, that means we can just return false because we can't match. Otherwise, we pop from both. So we can say opens, and then we can do this like remove last thing. So remove last and wildcards remove last. So we pop from both, and we keep doing that until our open parentheses are all matched. And if we were able to successfully do this, we just return true. All right, I think this should be it. Okay, there we go. So yeah, definitely this one is harder to come up with. I came up with the memoization, like, once you look at the constraints, the memorizations, like, if you've done DP, it takes like 5 minutes. So that's the one I would definitely go with in, like, an interview setting. This one is pretty unrealistic, I'd say, for an interview setting. Like, this is getting to, like, a hard problem. Yeah, but, I mean, you guys can let me know if this was, like, easier to come up with. The mistake I made in the beginning was I just counted the number of open and close parentheses, and I did make sure that, like, for every closed parenthesis, there was an open one before it, but it didn't really handle the wildcards correctly, and you do have to, like I didn't store their location, and then, like I said, if you have something like, you know, this, then, like, this is like I didn't handle this kind of thing. So yeah, that's why the locations matter. So here the time is oven, right? It's linear time, and the space. So we have two stacks that are both oven space. And yeah, like I said, there's an in-place solution where you have like a two-pointer solution. I think it's even less intuitive. And at that point, you're kind of like memorizing solutions to generic problems as opposed to like big picture concepts, where you can use a stack thing for a big picture concept, in my opinion. Where if you have like a bunch of things, you need to know the location, and you need to know like some things come before some things. You can use a stack. But yeah, that's gonna be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.